Imagine a rocket soaring from the desert, leaving a brilliant trail of light across the sky. That's the DF-61, a symbol of cutting-edge technological precision. In early 2025, a test launch from a desert region in western China captured the attention of aerospace technology researchers worldwide. A rocket was launched, traveling over 7,500 miles in a long-range trajectory, slicing through the atmosphere with steady speed and near-perfect accuracy. This was the DF-61, China's next-generation intercontinental ballistic missile, a masterpiece blending sophisticated mechanical design, advanced navigation systems, and cutting-edge digital simulation technology. This event wasn't just a technical test. It showcased how nations are pushing the boundaries of applied science, where artificial intelligence, innovative materials, and advanced simulation data converge to create major breakthroughs in the aerospace industry. The DF-61 stands as a vivid testament to an era where technology, not scale, is redefining capability and precision in the 21st century. Join Top 10 Discoveries Official to dive deeper into this incredible story right now. At the beginning of the year 2025, a single intercontinental ballistic missile launch captured the attention of global defense technology observers. That missile was the DF-61 a project developed over many years and revealed for the first time through a large-scale test above the skies of the Pacific Ocean. This was not merely a demonstration of launch and guidance capability, it was a milestone marking China's next leap in missile engineering and flight control, more than 4 decades after its last intercontinental test. According to publicly released data, the DF-61 was launched from a mobile platform, powered by solid fuel and guided by an advanced navigation system. Its trajectory reportedly reached beyond the Earth's atmosphere, covering a distance of over 7,500 miles before completing its test flight. The use of solid fuel drastically shortened preparation time and demonstrated rapid response capability, a key factor in modern missile systems. Most remarkable of all was the missile's stability and accuracy throughout the flight, showcasing the progress of next-generation inertial navigation and sensor technology. From a technical perspective, each DF-61 launch serves as a flying laboratory, gathering data to perfect its design. The missile successfully separated its stages while maintaining a stable trajectory, thanks to heat-resistant composite materials and sophisticated flight control mechanisms. These are the kinds of innovations usually seen only in advanced aerospace development programs. The test also sparked wide discussion about the integration of intelligent systems into missile technology. Analysts suggest that the DF-61 may have been equipped with a navigation processor using a basic form of artificial intelligence to predict and correct deviations during flight. If confirmed, this would make it one of the first missiles in the world to employ *** machine learning algorithms, *** for autonomous trajectory control, a direction currently being explored by several major nations. From a scientific standpoint, the DF-61 test not only highlighted China's maturity and design capability, but also reflected the global trend of aerospace technology convergence. Across nations, modern missile systems are increasingly built on shared foundations: mobility, high automation, energy efficiency, and safer operation. Within this evolving landscape, the DF-61 stands as a testament to technical progress, where precision and innovation define the new standard of the 21st century. The emergence of the DF-61 didn't happen overnight. It was the culmination of decades of meticulous research and testing. Following the completion of the DF-31 and DF-41 development phases in the early 2010s, China set its sights on a new generation of rockets with enhanced flexibility, superior precision, and optimized energy efficiency. According to publicly available technical reports, the DF-61 is a natural evolution of these earlier projects, but it adopts a more systematic approach focusing on automated navigation, orbital stability, and rapid response times. Research centers in northwest China are believed to have played a pivotal role in this process. This region, with its harsh climate, extreme temperature fluctuations, and varied terrain, provided ideal conditions for testing engines, simulating heat-resistant materials, and evaluating performance in real-world environments. At these facilities, engineering teams conducted extensive solid-fuel combustion experiments on a large scale, while leveraging pressure sensors and thermodynamic data to refine combustion chamber designs. The stability of solid fuel under extreme conditions was critical to ensuring the DF-61's high precision across its intercontinental trajectory. One of the standout features of its development was the use of digital simulation technology to replace many costly physical tests. Aerodynamic models were run on domestically developed supercomputers, enabling engineers to replicate the rocket's physical behavior under forces like friction, vibration, and temperature changes at altitudes above 60 miles. This allowed precise adjustments to the outer shell structure, thermal insulation layout, and thrust direction control, achieving error margins of just a few thousandths. Additionally, the integration of next-generation composite materials reduced overall weight, enhanced heat resistance, and extended storage lifespan, a critical factor for solid fuel systems. The initial goal of the DF-61 program wasn't just to extend operational range, but also to prioritize mobility and launch readiness across diverse terrains. With a mobile launch platform design, the system needed to maintain high stability, whether operating on soft ground, hilly slopes, or arid desert regions. This required seamless collaboration among teams specializing in mechanics, automated control, and aerodynamics, resulting in a rare interdisciplinary chain of innovations. As the development neared completion, the DF-61 emerged as a symbol of a new research paradigm blending simulation data, artificial intelligence, and real-world testing to optimize every detail. While specific details about the project's start date remain undisclosed, evidence suggests it was quietly initiated in the mid-2010s. Amid significant advancements in China's material and sensor technologies, in a broader sense, the DF-61 is more than just a feat of rocket engineering. It reflects a global trend in technological development, from automation and new materials to digital modeling. This project stands as clear evidence that technology, when synchronized across computational science and real-world experimentation, can compress decades of traditional research and set new benchmarks for the aerospace industry in the 21st century. The DF-61 marks a pivotal shift from traditional manufacturing to an era of complete automation and precision. Building on the foundation of the DF-41, this system has been redesigned to deliver superior performance, enhanced stability, and flexible deployment across all conditions. Structurally, the DF-61 employs 3 solid fuel stages, optimizing thrust without requiring manual fueling processes. Each stage is calculated for an optimal mass-to-thrust ratio, ensuring consistent speed from the initial phase. At altitudes above 60 miles, an automated navigation system, driven by inertial sensors and remote telemetry data, maintains flight trajectory with precision down to thousandths of a degree. A notable advancement is the cold launch technology, which uses compressed gas to eject the rocket from its launch tube before the engine ignites, reducing thermal stress and extending equipment lifespan. Paired with a mobile transporter erector launcher TL featuring an automated hydraulic balancing system, the DF-61 can be launch-ready in mere minutes across various terrains. The DF-61 is also believed to incorporate a multiple independently targetable re-entry vehicle MIRV system, allowing multiple warheads to navigate independently to separate targets. This requires highly precise trajectory control and mid-course correction technology, with laser gyroscopes and sensors continuously monitoring and adjusting for deviations during flight. The distinction between the DF-61 and DF-41 lies not only in its operational range, but in its advanced integration of data and artificial intelligence. The central processing system learns from prior flight data, autonomously adjusting trajectories and optimizing fuel burn rates to minimize errors and vibrations. In terms of materials, the DF-61 utilizes high heat-resistant carbon epoxy composites, reducing weight by 15 to 20% compared to its predecessors, while withstanding temperatures up to 5,400 degrees Fahrenheit during atmospheric re-entry. These improvements enhance flight efficiency, durability, and operational longevity. Overall, the DF-61 represents a seamless fusion of precision mechanics, digital simulation, and artificial intelligence. It embodies a new design philosophy. True power lies not in scale, but in control, self-learning, and optimization of every detail. The evolution from DF-41 to DF-61 not only introduces a new rocket model, but also reflects a global shift in engineering standards toward autonomous, high performance, and reliable flight systems for the future. In September 2025, during Beijing's Victory Parade commemoration, the DF-61 made its first public appearance, captivating audiences worldwide. The sight of mobile launch vehicles stretching along Chang'an Avenue was not just a display of engineering prowess, but a bold statement of homegrown advancements in aerospace technology. With its sleek, modern design, monolithic structure, and highly mechanized control systems, the DF-61 stole the spotlight, embodying a new approach that blends precision engineering with cutting-edge digital simulation and missile technology. The DF-61's debut was seen by observers as part of a broader showcase of comprehensive technological modernization. Alongside other achievements like the JL-3 submarine-launched missile, large-scale unmanned aerial vehicles, and semi-autonomous support robots, these systems share a unified design philosophy: technological self-reliance, integration of artificial intelligence, and high-energy efficiency. From an industrial perspective, this reflects years of investment in material science, sensor development, and navigation systems. The DF-61 was presented as a product of large-scale engineering and industrial organization, showcasing significant progress in modern missile design. Developing a system capable of high precision, utilizing solid fuel, and incorporating intelligent electronic modules highlights the maturity of China's mechanical and electronic industries. Analysts note that the DF-61's production process demonstrates a level of synchronization between design, manufacturing, and testing that aligns with the standards pursued by leading global technology powers in civilian space exploration. Beyond its technical merits, the DF-61's display carried profound symbolic weight. In a global context, prioritizing technological innovation, the image of a complex system operating seamlessly with thousands of mechanical and electronic components underscores the reliability and self-sufficiency of domestic industrial infrastructure. It also conveys a powerful message. Modern technological capabilities can be built through persistence, interdisciplinary research, and rigorous quality control, rather than relying solely on scale or financial resources. Many international experts view the DF-61 as a technical milestone rather than a purely military achievement. Analyses from independent research organizations emphasize that China's ability to design and showcase such a sophisticated system reflects a shift toward a high-tech economy where defense innovations often drive advancements in civilian applications. Technologies like jet engines and inertial navigation systems, similar to those in the DF-61, are already being applied in aviation, transportation, and industrial automation. The 2025 parade was thus more than a moment to celebrate a technical feat. It was an event that shaped a new image for modern industry. The DF-61, alongside other innovations, stands as a symbol of a technology-driven era where the boundaries between military research, space science, and civilian applications are increasingly intertwined. Within this landscape, the DF-61 is not an isolated achievement, but a testament to the integration of precision engineering, artificial intelligence, and industrial organization, reflecting how a nation is placing technology at the heart of its 21st century development strategy. Since its official unveiling, the DF-61 has sparked widespread analysis among global strategic and defense technology researchers. Notably, most discussions focus on its technical and engineering achievements rather than confrontational or political implications. Organizations like the Federation of American Scientists, the Center for Strategic and International Studies, the War Zone, and Euronews view the DF-61 as a testament to advanced precision engineering and high-level automation. Independent analyses describe the DF-61 as the latest generation of intercontinental ballistic missiles, fully utilizing solid fuel, a three-stage structure, and a multi-sensor navigation system. Some experts compare it to other modern ICBMs, such as Russia's RS-28 Sarmat, the United States Minuteman III, or India's Agni-V, highlighting similarities in design but differences in operational philosophy. While many nations prioritize expanding deterrence capabilities, China appears to focus on optimizing launch technology and system autonomy, evident in features like mobile launch platforms, self-diagnostic mechanisms, and pre-launch trajectory simulation capabilities. Engineers praise the DF-61's development as a significant leap in digital simulation and precision manufacturing. The ability to design and validate complex structures through simulated data has drastically reduced the need for physical testing, a feat previously achievable only by a handful of countries with powerful supercomputing capabilities. Experts from the Center for Strategic and International Studies note that this positions the DF-61 as a symbol of the digital design era in missile engineering, where data serves as a cornerstone for innovation. Additionally, analyses highlight the DF-61's standardized manufacturing and maintenance processes. Designed with modular components that can be quickly replaced, it significantly reduces maintenance time, mirroring trends in civilian aviation industries that use modular structures to lower operational costs. This convergence of civilian and defense industrial approaches makes the DF-61 a prime example of dual-use technology serving both security and applied science objectives. Some Western experts, while cautious in their conclusions, acknowledge that the DF-61 showcases China's ability to independently manage complex technical processes. The concept of technological self-reliance here extends beyond ownership to encompass integration, the ability to seamlessly connect design, production, and operational simulation within a unified data system. This remains a significant challenge even for leading global industrial conglomerates. However, analysts remain cautious about specific technical details, such as the DF-61's speed, maximum range, and precision due to the lack of comprehensive publicly available test data. Still, there is broad consensus that the DF-61's debut reflects a globalized trend in engineering science, where nations pursue shared goals advancing material science, simulation, and artificial intelligence to enhance the precision and safety of flight systems. Overall, international evaluations position the DF-61 as a technological milestone rather than a symbol of military might. It demonstrates the power of leveraging data, advanced manufacturing, and automated control systems elements shaping the future of the global aerospace and defense industries. From this perspective, the DF-61 is not merely a specific product, but a prime example of the convergence of science, technology, and modern engineering management, a field where the world is advancing together. Every major national technology program creates impacts far beyond its original scope, and the DF-61 is no exception. Though developed within a defense framework, its core technologies demonstrate remarkable potential for civilian applications, particularly in aviation, energy, and industrial automation. This reflects the clear trend of dual-use technology advancements that simultaneously serve security and socio-economic development. One of the most visible impacts is in the aerospace industry. Technologies from the DF-61, such as heat-resistant carbon composite materials, high-precision inertial sensors, and aerodynamic simulation models, are transferable to the design of aircraft, spacecraft, or hypersonic vehicles. The DF-61's ability to manage airflow and friction during atmospheric flight enhances the design of wings and nose cones, improving fuel efficiency in commercial aviation. This is why many domestic research conglomerates are now applying DF-61 simulation algorithms to civilian aviation projects and high-speed vehicle development. The energy and advanced materials sectors also benefit from related research. The DF-61's propulsion system required materials capable of withstanding extreme pressures and temperatures exceeding 5,000 degrees Fahrenheit. These materials have been adapted for use in gas turbines, civilian nuclear reactors, and small-scale jet engines. This synergy highlights an efficient approach, where defense research investments yield widespread value for the energy and industrial manufacturing sectors. Another notable advancement lies in the DF-61's inertial navigation system, INS, and real-time data sensors. Critical components of the rocket, this technology is now expanding into maritime navigation, autonomous vehicles, and industrial robotics. These systems can operate without full reliance on satellite signals, enhancing safety and precision in harsh environments. Scientifically, this marks a step toward next-generation autonomous technology, where devices can independently determine position, direction, and decision-making through behavioral analysis algorithms. The philosophy of dual-use technology serving both military and civilian goals is vividly embodied in the DF-61. Industry experts note that adopting this model has fostered an innovation ecosystem linking research institutes, factories, and universities. From machine learning algorithms for missile navigation to trajectory prediction models applied in logistics, This technology transfer showcases a natural convergence of science and market needs. The DF-61's influence also extends to smart manufacturing and industrial robotics. The integration of pressure sensors, feedback mechanisms, and real-time data processing systems has become a standard in automated production lines. The DF-61's operational model collecting, processing, and responding to data in milliseconds serves as a prototype for modern robotic systems. From automotive assembly lines to driverless transport vehicles, the broader picture reveals that the DF-61 is not just an aerospace achievement, but a catalyst for uniting scientific research and industrial innovation. Advances in materials, digital simulation, and artificial intelligence developed for the DF-61 are now driving production capabilities across multiple civilian industries. This demonstrates that when technology is built on interdisciplinary knowledge, its value transcends a single domain, permeating the entire industrial framework and fueling a global era of automation and intelligent systems. The technical achievements of the DF-61 extend far beyond a single system, paving the way for a new decade of precision-oriented technology. The integration of artificial intelligence, satellite data, and global sensor networks is steadily forming a complete automation ecosystem where flight systems, spacecraft, and unmanned vehicles can communicate, learn, and optimize their paths independently. The DF-61, with its ability to control trajectories using machine learning models and process data in real time, serves as a testing ground for this transformative trend. In the near future, technologies derived from the DF-61 could further enhance space programs and atmospheric research. The pressure sensors, thermal measurement systems, and vibration control technologies developed for high-altitude flight can be adapted for climate monitoring, asteroid detection, or small satellite launches. The DF-61's airflow simulation models could also help scientists better understand stratospheric wind movements, critical data for aviation and global weather forecasting. Another promising direction lies in multi-layer data connectivity and processing. Future launch systems will no longer operate in isolation, but will be integrated into unified control networks. Real-time synchronization of orbital data, radar, and satellite imagery will enable control centers to optimize launch paths, reduce errors, and conserve fuel. This technology could also find civilian applications, such as managing air traffic or coordinating autonomous vehicles in complex environments. Experts predict that over the next decade, the field of precision navigation will see a convergence of space technology, artificial intelligence, and material science. Advances in deep learning algorithms, quantum sensors, and ultralight materials will enable flight systems to maintain exceptional stability in harsh conditions. In this landscape, the DF-61 stands as a technical milestone where concepts of autonomy, intelligent sensors, and optimized control are unified into a cohesive framework. Beyond aerospace, the principles behind the DF-61 could help develop self-operating systems for planetary protection, from monitoring cosmic radiation to guiding climate research or interplanetary exploration missions. The ability to automatically analyze data, predict errors, and adjust in real time will become the standard for devices operating in space and on Earth. On a broader scale, the DF-61 illustrates how a nation can shape global technological progress through engineering innovation. When simulation, design, and manufacturing capabilities are integrated within a single ecosystem, the boundaries between civilian and defense technologies become more fluid, fostering international collaboration in research and technical standardization. The future of precision-driven technology lies not only in speed or power, but in system reliability, connectivity, and learning capacity. Each new generation of devices will carry forward elements of the DF-61's technical legacy, from its data-driven design philosophy to its near-absolute precision in flight. As humanity pushes toward the next frontier of science, systems like the DF-61 serve as a reminder. Technology knows no borders, only the shared aspiration for perfection. The DF-61 is more than just a rocket. It's a symbol of modern technology's maturity, where material science, digital simulation, and artificial intelligence converge seamlessly. Every technical detail reflects humanity's ambition to achieve absolute precision, showcasing how data and creativity can be transformed into tangible power. In an era where technology is becoming the universal language of humankind, the DF-61 embodies relentless innovation and the pursuit of perfection. What do you think will be the next breakthrough to define the new era of modern technology, artificial intelligence, green energy, or space exploration? Share your thoughts in the comments below. Don't forget to hit subscribe to stay updated on the latest insights into technology, national strategies, and innovations shaping the future. Top 10 Discoveries Official will return with untold stories, boundary-pushing projects, and quiet revolutions with global impact. See you in the next video.